Hello, students. We are going to be working on our first lesson in our new unit, which is studying polynomials. And so this lesson is just looking at single term polynomials. Those are called monomials. And some of you may have already been provided with the exponent rules that I'm displaying on the screen right now. Some of you may wait and get those when we have the lesson in class. But you do have a reference sheet that will either already be provided or will be provided for you that has all of the exponent rules that we'll be using as we simplify monomial expressions. So you'll notice that we are doing a lot of work with exponents. So I want to make sure you know what I'm referencing when I talk about an exponent. We'll be looking at the base, which is the part that is raised to the power, and then the exponent looks like a superscript, so it's written off the line up above the base, and the whole expression taken together is called the power. So you'll have this type of expression when we work with exponent. That if you have x to a power, then that means that you take that base to that, you take that base and multiply it together however many times the exponent says. So n times is how many times you would multiply all that together. Okay, and that's what exponents will do. So we'll do just a few definitions. A monomial is a number or a variable or a product, which means multiply, of numbers and variables. So examples of monomials, you could just have a number like 5. You could just have a variable like x, or you could have a product of that number and that variable, so 5x, or it could be a product of multiple variables, like you might have 3x to the second y. That would also be a monomial. I have a few other words that we'll look at. A constant is just a number, like 3. 3 is a constant. You know, you can have bigger ones, 200. You can have negative ones like -5. A coefficient is the number multiplied to a variable. And we might really, mathematically, we should say it's the numerical factor of a term. So the numerical factor of a term. And examples of that, so the number multiplied to a variable. If I give you the expression 4x to the second power, the 4 would be the coefficient. So it's that number that's written in front. If you have just x as your variable, then the coefficient is an understood 1. So even though we don't write the 1, we understand that the coefficient is a 1. We'll do just a little bit with this next definition, the degree of a monomial. And you can find the degree of a monomial by adding the exponents of the variables. And so if we take a look at our first one, 2x to the fourth, y to the second z, we have an exponent of 4, an exponent of 2, and an exponent for the z of 1. And so this would be a degree of 7. And if we don't have any variables, then the degree would be a 0. So our next one is just the constant 5, and there are no variables. So that would have a degree of 0. For this course, we will not do a whole lot with degree, and I don't want you to think that we normally add the exponents all together to do any simplifying. That's just to tell what type of monomial you are working with. So this is your introduction to some of the vocabulary. The rest of what we will do will be examples. I'll be working your examples and then referring to the rule sheet that I showed you on the beginning screen. So we're looking first of all at multiplying bases together. And when you multiply bases together, the rule is, so actually I'm going to have you look at rule number 2 up here. If bases are multiplied, you keep the base and add the exponents. So it's kind of a two-part process. Keep the base, add the exponents. And then you will be provided with examples to look at on this formula sheet. So I'm going to scroll and get to my examples here that we're working with and clear the sync off. So for our problem, we have a to the fourth times a to the second. So we have the same bases. We will keep the base of a, and then we're going to take those two exponents, 4 and 2, and add them so that we would get a simplified answer of a to the 6th power. So a to the 6th power would be our final answer. You do not have to show the addition of the exponents, but if it helps you, then certainly do show that. On problem 2, you have multiplication of two monomials, but they have coefficients. So you would want to multiply the coefficients together, so the -2 and the -5, and then we take the a's and we want to add their exponents. So in this term, or in this factor, we have a to the third, and in this factor, we have a to the first. So we would add the 3 and the 1 exponent for the a. And then for the b, for our first term, we have b to the first, and then in our second one, b to the fourth, and that would be added on. So that -2 and -5 would make 10. So they're numbers, they're coefficients. You treat numbers like numbers. And then exponents have their own rules. So a would be to the 4th power and b to the 5th power. So the monomial becomes 10, a to the 4th, b to the 5th power. So that's for multiplying. We'll look at dividing next. So for dividing exponents, and again, I'm going to scroll up and take a look at our rule sheet. So for dividing exponents, that's rule number 3. When you get this form, you can look at it. And what the rule says is that you keep the base again, but when you're dividing, the exponents will subtract. So we will subtract the exponents. I do want to point out that in this example, the 8 and the 12 are not exponents. And so those are just treated as a fraction that gets reduced. So the 8 will divide by 4 and become 2. The 12 will divide by 4 and become 3. And notice how you have the 2 over the 3 in the next line. And that's different from dealing with the exponents. So the exponents we will subtract. So I'm going to move back to the examples from your notes about dividing. So when we divide, we're going to subtract the exponents. Now, actually, this first example brings up something else that does happen. You could run into negative exponents, which is what rule number 7 is about. And if you have a negative exponent, then the base will be changed to its reciprocal, and it will make the exponent positive. And so I like to think of it as the base moves. So if it's in the numerator, it moves to the denominator. And when you move the base, it becomes a positive. And I'm going to try to show you that as we work through that first division example. So on the division example, you have s to the second power divided by s to the 10th power. I'm going to show you a couple of ways to think about this. So if I just strictly want to go by the rules, then I would keep the base and take my exponents and subtract them. So 2 subtract 10 would give me s to the negative 8th power. And then according to the rule, so I have s to the negative 8th over 1. According to the rule, I have a negative exponent. I would have to move that base to the denominator, make my exponent a positive, and I can't have a denominator without a numerator. So I would have a numerator of 1, and my final answer would be 1 over s to the 8th power. Now, I'm going to give you an alternative solution to this that I think will make more sense. And it would be, I think, something that you would more naturally do. So the way I like to look at a problem like number 3 is thinking about what exponents mean. So an exponent means, for example, s to the second means s times s. And s to the 10th means that I would have to write out 10 s's. So I'm going to do that. So I've written out 10 s's all multiplied together. And when you have that, you can cancel. So we can cancel an s for an s. That leaves a 1. We can cancel an s for another s. That leaves a 1. And so I end up with a 1 on top and 8 s's on the bottom. Well, there would be a quicker way for you to get to that answer. So the quicker way would be, so I'm going to start over. I have s to the second over s to the 10th. I'm going to use my rule about exponents, which says that when you're dividing, you subtract. So I'm going to subtract those two exponents. I'm going to take 10 minus 2. However, my larger number is in the bottom. And notice that when I subtracted, I took my larger number 10 minus my smaller exponent number 2. So I took 10 minus 2. That's 8. I'm going to keep the base in the denominator because that's where the larger exponent was. I subtracted 10 minus 2 to get 8. And then that completely wiped out the numerator. So I would have a 1. So this is 1 over s to the 8th power. Let's take a look at number 4. So number 4 has 6 over 3, and then it has the s to the 12th over s to the 4th. So we want to treat numbers like numbers. The 6 over 3, 6 divides by 3, and we get a 2. Your bigger number's on top, so that's where that 2 goes. Now, for your s's, you have the bigger exponent on top, the smaller one on the bottom. So we're going to take 12 minus 4. And actually, I just don't think that it really helps to show that step, so I'm not going to. So 12 minus 4 is 8. That's your exponent. And now the denominator is gone. So we'll put a 1, but we never leave just a 1 in the denominator. So 2s to the 8th would be our final answer on that. Then we'll move on and look at a power of a power. So I'm going to take us back to our exponent rules at the top. Rules number 4 and 5 deal with taking a power and raising it to a power. And for these rules, we will multiply the exponents. So you'll notice here, the exponents will multiply. The base stays the same. The exponents multiply. If you have a parentheses with a power outside the parentheses, the exponent, you might think of it as distributing. The exponent will multiply by any other exponents, including if something has an exponent of 1. So, for example, on this one, you'll have negative 2 to the 1 times 4 power. You'll have x to the 3 times 4 power and y to the 1 times 4 power. So you can see that in this example right here. And negative 2, I might just point out, to the 4th power means negative 2 times negative 2 times negative 2. So notice that I'm putting it in parentheses, times negative 2 times negative 2. Something to the 4th power means I'm taking it times itself 4 times. So negative 2 times negative 2 is positive 4. That answer times negative 2 is negative 8. And that answer times negative 2 is positive 16. So, so we're getting the idea of what an exponent means, as long as well as some of the rules for dealing with it. So if we look at your examples, going back to those, we have a power of a power for number 5, where the exponent 3 will distribute to everything inside that parentheses. So that means we'll start with negative 3 to the 3rd power. Then we'll have the c. It already has an exponent, and so that exponent will multiply by the 3. And the same thing for the d. The d already has an exponent. That 5 will multiply by the 3. So negative 3 times negative 3 times negative 3. That's what this means. And so that'd be 9 times negative 3, which would make negative 27. And then we have c to the 6th power and d to the 15th, all multiplied together. On number 6, you have 2 negative exponents, but let's deal with getting rid of the parentheses first. And I like to think of it that way. Whenever you have parentheses with exponents, remove the parentheses first. So if we remove the parentheses, we would multiply these exponents. We have c to the 10th power. Let me go ahead and show what I did there. So I took -2 times -5, and that would be c to the 10th power. My exponent is no longer negative, and so I would just leave my answer like that, c to the 10th power. All right, so looking at your next section, negative exponents. Now, we touched on this briefly, but I want to keep going back to it. So number 7 starts to follow my idea of if you have a parentheses, remove the parentheses first. So on number 7, now I have a fraction, so I've got to keep that fraction. I have -2, and this 4 power will be an exponent for the -2. Then I have a. Well, the 4 is also going to be an exponent for the a. Then in the denominator, I have b, and I have -2, but I have this 4th power on the outside, so we'll multiply. -2 times 4 gives me -8. All right, so now I'm going to think about any exponents that I have. First of all, I have -2 to the 4th power. Now, we did that just a minute ago, but I'm going to revisit it. That's meaning -2 times -2 times -2 times -2. So the first ones would give me 4. 4 times -2 would give me -8. And -8 times -2 would give me 16. So on top, I have 16. Then I have a to the 4th. Now, I have a negative exponent on the bottom. If you have a negative exponent in the denominator, you'll move it to the numerator. And when you move it, the exponent becomes a positive. So, and then your denominator has nothing left in it than a 1, and I don't want you to write that 1. I just want you to leave it like this, 16, a to the 4th, b to the 8th. Okay, so I'm going to continue on with number 8, using my idea that I want to remove the parentheses. So I'm going to take the -4 and distribute it to, first of all, the x. So we'll have x to the -4th. And then I'll also be distributing the -4 to the 3. So over 3 to the -4th power. So I'm distributing and getting rid of the parentheses. So I think this is the best illustration I've done so far for negative exponents. Negative exponents move. So if you have a negative exponent in the numerator, then you move that whole expression, the base and the exponent, to its opposite position. So this x to the -4th is in the numerator. It's going to move to the denominator with a positive exponent. And then likewise, if you have a negative exponent in the denominator, then that whole base and its exponent move, but when you move it, you get a positive exponent. So then 3 to the 4th power means 3 times 3 times 3 times 3. And so these first two are 9, these two are 9. 9 times 9 is 81. And your final answer for this one, 81 over x to the 4th power. So notice that I got rid of the parentheses first. And then after removing the parentheses, then I dealt with any negative exponents that I had. Okay, so again, a negative exponent moves. If it's in the denominator, you move the entire base to the numerator, change your exponent to a positive, and vice versa. If it's on top, you move it to the bottom and make your exponent positive. Okay, we have one other special kind of exponent, and I will go back to our rule sheet. Number 6, if you have a 0 exponent. So if your exponent is 0, then you replace the entire exponential notation with the number 1. So you can see I've got 4 to the 0 power, just becomes a 1. Now on this one, the x to the 0 is the only thing that has the exponent of 0. The 3 doesn't have it, the y doesn't have it, but notice that the x to the 0 power becomes a 1. So let's move to look at your examples, starting with number 9. Now, I might make a note that the negative sign on number 9 is not affected by the 0 power. So if it doesn't have parentheses on a negative, then you have to keep the negative. So we will keep the negative, and then 7 to the 0 power, any base to a 0 power is a 1, okay? And I might just show you, this is a little extra example. If I would have had the negative 7 in a parentheses to the 0 power, then the 0 power does affect both the 7 and the negative, and that would just have become positive 1. So just so you can see the difference in when we do or do not have a parentheses. And then number 10, we have negative 21 x to the 0 power. The negative 21 is not affected by the exponent, but the x to the 0 power is a 1. The x completely goes away. The power goes away. It just becomes a 1. Negative 21 times 1 is negative 21. So hopefully, as you are working through these exponents, you will remember to refer to your exponent rule sheet and keep in mind what an exponent means.